from the Gujarat University, Gujarat. Yeah. Let me show the from where I am. Yeah. Yeah, here we are over here, yeah, at the Bangalore, and I am from this place. Yeah. So let us move to the our subjective part. Yeah. That is, before I start, I will acknowledge the support which I have received so far for this particular kind of work. My research group and my university, the funding agencies from the government of India, that is DST FIST and DRSF programs, and the program organizers of this particular workshop, Professor Abhishek Dhar and the ICTS, for providing me the funds to come over here and to share my results with you. Yeah. I will try to discuss the results which we have simulated at our place. Okay. First, before starting with the linear mass graded chain, I will show first few slides for the harmonic and anharmonic lattices, and then we will see one by one the results which we have for the linear mass graded chain, exponential mass graded chain, diatomic chain, of course, as usual. Okay. Then the mass defect chain. Okay. Abrupt mass junction thermal diode, or the composite materials, then the sandwich structure, and the results for the transistor, that is the thermal transistor. Yeah. The first two slides, as I told you, that is the very basic and the very preliminary things. Of course, that is, if you start to simulate the heat conduction problem, that is why I am showing this, is that we have developed the codes, and to verify whether the codes are right or wrong, okay, we have first of all constructed these kind of simulations. Yeah. And we know that is, if the chain is connected with the higher temperature bath and the lower temperature bath, and if we consider the harmonic model, we do not have the temperature gradient between the chain. Okay, and the temperature will be the average temperature of the higher temperature bath and the lower temperature bath, and hence the law remains invalid. Yeah. And then, of course, as usual, okay, then one has to think about the anharmonic model, and when we consider the anharmonic model, we have the Fourier law. Yeah. Then the thermal conductivity, again, this is the well-known fact. Yeah. That is the thermal conductivity in the anharmonic model. If we don't consider the on-site potential, that is the interaction with the substance or any substrate or any external field, okay, then the conductivity moves like this. Okay, versus the chain length, versus the system size. And if you consider the interaction, that is the on-site potential, then the conductivity is this. Yeah. Of course, again, there is a controversy for the exponent alpha in the conductivity versus the system size, and we have the various values of the alpha available in the literature, starting with the alpha is equal to 1 for this model, 0.5, alpha for FK model it is between 0 and 1, and so on. Okay, this is the literature values. Then comes the concept of the linear mass graded chain, then exponential mass graded chain. Of course, to get the Fourier's law, that is to get the temperature gradient, we need the anharmonicity in this particular part. Okay, so here the concept is the linear mass graded chain and the exponential mass graded chain. That is the first particle. The mass of the first particle we have taken, and let us say the higher mass, and this mass is the lower mass, and between this we have changed the mass. And for that, very simple equations we have used. Okay, that is the suppose m for the linear mass graded chain, m at a point I is given by m0 plus mc into xi. Okay, this is for the linear mass graded chain, and we have to find out the two constants. Okay, by using the two conditions, that is the at x is equal to 1 and at x is equal to n, two masses are known, and based on this you can find out the constants involved over here. Similarly, for the exponential mass graded, we have used m of I is equal to m0 e raised to minus lambda xi. Okay, where again we have two constants, and we have varied the mass exponentially within this chain. Of course, the results for the linear mass graded chain are already available previously by a group of people from the National University of Singapore. Yeah. So first, okay, in the exponential mass graded chain, okay, when this higher mass is connected to the higher temperature reservoir and this is at the lower temperature bath, we have the this kind of temperature profile. And if we reverse this, that is because the asymmetry is there, okay, then we have this temperature kind of characteristics, okay. Yeah, next. Then we have compared the results with the linear and the exponential mass graded chains. So first part, okay, I think the result over here is missing. Yeah, I don't know why. Yeah, yeah. Sorry for that. Yeah, I have checked before the loading, but unfortunately this is not visible over here. Yeah. So these are our results. That is, if we find out the this is the heat flux and this is the temperature of the lower heat bath, then see here, okay, we have the negative temperature difference, okay, that is the negative differential thermal resistance over here. NDTR we can observe over here. In comparison with the linear mass graded chain, okay, the region, this particular part is, okay, elongated, that is this region is a little bit higher than what we see, okay, in this linear mass graded chain. Okay. Not only this, okay, if we compare the results of the thermal conductivity against this chain length, yeah, then over here, okay, this line is for the linear mass graded material, okay, and this line, okay, the results are for the exponential mass graded chain, okay. These are the results of Young, yeah, Young et al. And for that, the conductivity, thermal conductivity comes out to be of this kind, 0.027 N and N, okay. And this is the results for us, that is K is equal to 0.045 N, okay. So in comparison to, you can say, if we have the mass graded chain, that is the linear variation that is of mass, in contrast to that, if we have the exponential variation of mass, then the thermal conductivity of this kind of chain is higher than the linear graded material. We have also studied the thermal rectification in the exponential mass graded enharmonic lattice, okay, and this is the delta, that is the bias is positive when this bath is this particular end is at a higher temperature and this particular end is a lower temperature. This normalized heat flux is like this. And when we reverse the position of the chain or we change the position of the heat bath, then the flux is decreases in direction, okay. So in our case, in this particular part, we have the rectification of 70 to 75%. Yeah, please. Size of the system. It is 0.0 in this particular case. Yeah, the size dependency is this. Rectification. Yeah. Oh, that we have evaluated the size dependence of the rectification with the mass. Okay, we have kept over here the length of the chain fixed in this particular case while evaluating this particular part. It depends on the size. Yeah. Okay. Then, of course, whether this kind of simulation remains valid at the experimental side or not, okay, we have the evidences, that is, if we have the nanotube, okay, this is the carbon nanotube and these are the two sensors. First of all, it was the same mass over here, and then the mass is deposited over here to create the mass graded system over here, okay, and they found the thermal conductivity previously in 2006 that the rectification over this kind of variation is 3 to 7%, while in the exponential mass graded chain and in the linear mass graded chain it was 11%, while in the exponential mass graded chain it was 70 to 75% depending on the different parameters. So again, this is the schematic which the experimentalists have done the work. Yeah, let us move. Then, of course, this is the traditional one, that is the diatomic lattices. Of course, there are three different cases. One is to see over here, that is, if the chain length is of even particles or even oscillators, okay, that is higher mass, lower mass, higher mass, lower mass, and so on. And second part, that is if you start with the lower mass over here, higher mass, lower mass, higher mass, and then the higher mass like this. That is when you connect the system, that is the heat bath, higher heat bath to the higher mass and the lower heat bath to the lower mass. That is the one situation, or the other one. Similarly, if the number of particles are even, okay, then the first end will be, if of higher mass, then the last end will be of lower mass. And if the number of particles are, let us say, not even, okay, odd, then both the ends will be of same mass. Then the situation will be different. Okay, the temperature profile and the result will be little bit different. Here we have considered the even mass system, that is even number of chains, particle chains, and our temperature profile looks like this. Okay, this for the harmonic model. Though, of course, there is a mass is not equal. Okay, that is the diatomic chain. The interesting phenomenon, of course, everybody has observed, but nobody has pointed out, that is the temperature profile is always remain higher than the average temperature of 2 heat bath. Yeah, that is the higher than the average temperature of 2 heat bath. If you split, okay, then this is the temperature profile for the lighter particles, and this gives the temperature profile for the heavier particles. Okay, heavier particles, and we do not have, okay, the temperatures, that is no particle have the temperature between this range. So of course one can use even this diatomic chain for the phonon filtering. Yeah, phonon filtering. And then, yeah, this is the for a small runtime, okay, which I have taken, so you get the very wide oscillations over here. If you take the enough long time, let us say 10⁶ or 10⁷, then even you can remove in the enharmonic diatomic chain. Okay, that is in the harmonic chain we do not have the temperature gradient, while in the enharmonic diatomic chain we have the temperature gradient. Yeah. Okay, go ahead. Then these are the results for the flux and versus the chain length. Flux versus the chain length. Yeah. And as you increase the number of particles, that is the flux, heat flux decreases. These are the two results for corresponding the monoatomic lattices. That is m is equal to 2 and m is equal to 1. Okay, we have considered in the unitless dimensionless system. This is the for diatomic. Then if we consider m is equal to 2, okay, that is the this one, and m is equal to 1, this one. Yeah, and in both, see, compared to the monoatomic lattices, the flux for the diatomic lattice is less, okay, is lower. And then we have seen plotted the conductivity over here versus the chain length. Okay, the same conclusion over here, that is here. This is the conductivity for monoatomic chain. Again, this is the conductivity versus the size dependence conductivity of the monoatomic chain. And these are the results for the diatomic chain. Of course, with our system, we are able to compute or simulate the system size up to the 6400. Okay. And then we try to, okay, let us say if we extend the system size higher than this, because see, the gap between these two monoatomic chain is uniform, but the gap between these, okay, is not uniform. As you move away, the separation between the two lines decreases. That is, the conductivity is trying to merge towards the monoatomic system. Yeah, and hence we have extended this curve, okay, from 10,000 to 1 lakh, okay, and we see that this diatomic, the conductivity of the diatomic system at the higher chain length crossovers, okay, over here and over here to the constituents particles. I don't know whether it is possible experimentally or not, but this is the results which we got over here from this particular part. Yeah, the power divergent exponent of the thermal conductivity, which comes out to be 0.248, and the diffusion coefficient comes out to be 1 to 8 in this diatomic lattice. Okay, this is the conductivity for various mass segments, that is mass of the 1, then mass 2, 2.5, 5, 10, and different for the different masses. So as you increase the mass of the heavier particle in comparison with the mass of the lighter particle, then the conductivity decreases. Then the conductivity decreases. Yeah, conductivity decreases. Yeah. Then effect of the defect. See, if we have the monoatomic lattice, then okay, what is the importance or what is the effect of the defect if we produce a defect either removing the mass or replacing the mass in that particular chain? Okay, we can even substitute the mass over here. We have studied over here the effect of the defect, that is the defect position, and as well as the mass of the defect. Okay, that is whether it affects or not. Then for the harmonic model, again, see, when we consider the harmonic model and if we substitute a defect at a, let us say, lattice site, if we have the chain of the 200 particles over here and the lattice site is 50, that is the defect I have kept at a 50, yeah, then the defect I have kept at a 100, this line, okay, this curve, and then the defect I have removed from here and placed at, let us say, place 150. So 3 different configuration I have tested over here, and depending on that particular position of the defect, we have the different scenario in the characteristics. Okay, over here, see, when the defect is towards the higher heat bath, okay, the temperature of that particular oscillator, this particular defect particle seems, okay, it is higher than even the temperature which we have applied through a reservoir. Okay, so we are unable to still find out the proper explanation, that is why the temperature over here is much more higher. Similarly, even when this particular part defect is at the center of the chain, okay, again the temperature, of course, there is a revulsor of this particular part, and again this temperature, this particle is much more cooler than the temperature of the lower bath. See, this temperature comes out to be 0.5 in the dimensionless unit compared to the 0.9, yeah. Of course, our experiments, this experiment suggests that this particular peak, okay, it moves like these, and these, okay. This gives us a smooth curve. Depending on if you shift the position of a defect from here to here, then we have a nice, you can say, more or less the sinusoidal kind of curve over here. Okay, yeah. We are, of course, searching a proper explanation, that is why the temperature, okay, comes out to be much more higher or lower than the temperature of the heat bath. Okay, let us move. Then when we apply, that is the anharmonic model, that is a PU beta model we have applied over here for the diatomic case, yeah, and the defect at the center, So, and we have taken the different masses, that is the mass of a diatomic, this particular defect is, let us say, 0.5, then it comes to be 2 and it is 3, okay, then this. So as you increase the mass of the defect, we have, okay, a temperature jump over here. It means that the defect, okay, creates the interface over here, and okay, that this temperature jump depends on the mass of the defect. Okay, then the same defect we have placed at a point, let us say 150, the same kind of results we obtain. That is, the temperature characteristics jump is higher for the higher mass defect. Yeah. Then we have tabulated the numerical values for the these defected materials. That is, the defect is of the 0.5, defect is 0.2, and the mass of the defect is 0.3, and the position, this is reflected the position of the defect of 200 particles chain, that is at the 50, at the 100 and 150, like this, and then the thermal conductivity of chain. See, if you see that, then as this size, that is the mass of the defect and the position of the defect, also depends, also influence the conductivity. That is, the conductivity of the material, this defected material, increases, okay, over here as you, okay, pour the defect or create a defect or substitute a mass, okay, towards the lower heat bath, okay. The same more or less conclusion, except this, okay, that is over here, see, for this it is 0.85, while the fraction comes over 0.75. So we are trying to simulate again this kind of result, and we are going to verify whether the uniformity in the relation, that is, as you move towards the lower heat bath, that is, if you create the defect towards the lower heat bath, then the conductivity increases, for generalizing this.
So here the unit mass is 1?
Yeah, that 1 and 0.5, okay, the normal chain, that is mass is 1, and then the defect is half the mass of the, and then twice and then thrice kind of this, yeah. Then again, next part, that is the abrupt junction thermal diode, okay, or the composite material. We have made the junction between the two different materials. Of course, few results and the few techniques are shown by the previous speaker, Professor he, yeah, okay. This was the model for the thermal diode, okay, and we have, okay, the temperature jump. This is the monoatomic chain, okay, the temperature profile for a monoatomic chain, and for the different masses, that is over here, the right mass is 1 and the left mass is 1 and the right mass is 1.5 and 1, okay. For that we have the different characteristics. Of course, okay, like we have created this kind of composite by varying the different size. That is, on this side we have, let us say, a 10 oscillator, and on this side we have the 90 oscillators. That is the total length of the composite we have kept as 100 units, and out of these 100 units the first part is 10 and the rest part is 90, then 20, 80 and so on, okay. And then we have the temperature characteristics. This, the important feature over here is this, okay, see, the curvature of this part, see, over here it go down, okay, and then bounce back, the temperature bounce back, and again it goes to this. So the negative temperature gradient seen over here, which is evident from this particular part, okay. So that as the size of this particular left segment increases compared to the this right segment, then this kind of feature is seen, okay. This is the conductivity versus the size of the left segment. That is, if we have the 10 oscillator on the left side, and then the conductivity is this, and if you increase the size of the left segment compared to the right, then the conductivity decreases. Again, this is the nonlinear trend over here. We do not have the linear relations between the size and the conductivity over here. Next. Then the mass effect, that is, we also studied the effect of the mass, okay, of two different segments, okay. We have kept the size of the two materials same, that is the 50 on the one of the side and the 50 oscillators, or the 50 on the other side, and we have varied the mass ratio of two segments, okay, and for that we have simulated the various temperature profiles. And this is the ITR, that is interface thermal resistance, we have computed, okay. The ratio, when the ratio of the two segments is 1, we have the minimum resistance, okay, and this is again the non-uniform, okay, it is not the uniform curve on both the sides, yeah. Initially, as you increase this mass ratio, this resistance is decreases, and on further increasing after a 1, okay, it starts to increase. And this particular behavior is again not uniform. Asymmetric curve we obtain over here. The same is reflected over here, and in the conductivity, Okay, so if we have this kind of phenomenon, then even we can find out that, let us say, if we want to prepare a material which have a conductive, which possesses a conductivity, let us say this, then how to prepare? That is, if we have this kind of segment with this and the other kind of segment of this mass with this, you can scale the conductivity. Yeah. Then comes the diode part. Okay, here we have given the few terminology over here. That is, when HM is the segment of the higher mass and LM means the segment with the lower mass, that is higher mass segment and lower mass segment, like a p-type material and n-type material into the electronic diode. So this is H-type material and this is L-type material. Okay, when H-type material is connected to a higher temperature bath and the L-type material is connected to the lower temperature bath, then it is known as the forward thermal bias condition. Forward thermal bias condition. Okay, and when we find out the flux over here, okay, in the forward bias condition, forward thermal bias condition, we have the conductivity is increases. Conductivity is increases. Okay, the next, that is, when the higher mass is connected to a lower temperature and this lower mass segment is connected to a higher temperature. See, TL is less than TR, and I have also reworded the symbol like a battery symbol in the PN junction diode. And in this situation, the conductivity curve comes out to be this. And hence, for this particular material or this particular simulation, the conductive versus the bias potential, okay, is this. This is the forward bias thermal, and this is the case for the reverse bias. So this gives us the characteristics like our PN junction diode. Of course, this kind of work is already there and which supports our simulation. Yeah, this is the rectification rate in the conductivity for this kind of it increases, okay, as you increase these mass differences. Then we have simulated the results for the sandwich structure. That is, instead of preparing a composite with the two materials, okay, diode, okay, we have added one more material between these two. Okay, so these two are of the same kind, and this is represent the different kind of material, and this is the sandwich structure. So the sandwich, it means that the upper layer and the lower layer, okay, that is the upper and the lower layer are of the same kind, then it will be a sandwich, okay, and some filling is there between these two layers. Yeah. So the results are this over here. This line, okay, we have the temperature jump over here, okay, these and these, and then this, okay, like this. So again, it also depends on the mass of this particular and the size of this particular sandwich structure, this filling in part. Yeah, this is the flux to show that is whether our calculations are okay, stable or not. That is the here for the monoatomic system, the thermal conductivity comes out to be of this order, okay, okay, and when we have this sandwich mass, okay, mass of the sandwich structure is this one, 0.1, okay, then on this side, we have calculated the temperature gradient over here and over here towards the two sides of the sandwich structure, that is filling part. Okay. For this, the temperature gradient is of the order of 10⁻², and it slightly increases over here. Similarly, the ITR, that is the interface thermal resistance, okay, of the first part over here, okay, over here at this particular junction is this, while over here it decreases, okay, and the thermal conductivity of the sandwich structure, decreases in comparison with its constituent particles. Yeah. Then see, in the sandwich structure we have the three different materials and two heat paths, and we have rearranged this particular part analogy to create the thermal transistor. Yeah, this is our model of the thermal transistor. Yeah. Okay. And of course this here, okay, this part, see, our transistor becomes on, okay, if you apply the temperature bias this, okay, and remains on up to this point, and here the two currents, that is the current through the gate segment, source segment and the drain segment becomes equal. It means that here we will get the unitary gain kind of results. That is, you can have the amplification as well as the switching effect in this particular part. Yeah. Then the interesting part for this thermal transistor are the characteristics of a thermal transistor, and over here our concept is this, that is, between these two segments, drain segment and the source segment, we have applied the temperature difference and we have kept the temperature difference between these gate fixed, like a transistor or the fat circuit where we used to put the VG fixed and we used to vary the VGS. Okay, so we vary these and these, and we have obtained the thermal characteristics of a thermal transistor, okay, like this. This is known as the output characteristics, okay, that is the output current versus output temperature. Okay, and our simulated results are these, and for the first time we are coined the words very analogous to the FAT terminology, that is, where this current increases linearly, okay, in the FAT circuit, in the MOSFET, it was known as the ohmic region, while here instead of ohmic region we have termed this as a thermal Fourier region. Okay, this is the Fourier region where, okay, the Fourier flow remains valid. Then the curve bands from here, that is the heat current flowing in this direction, try to decreases, and that part we have given the name the thermal knee point. Then this is the pinch off point, and then this part is the saturation region. This is for when the difference TGS we have kept 0, okay, and then we have increased this negative bias, that is, we have simulated this kind of characteristics for various TG over here, okay, and the curve is this, that is, for TG is equal to 0, then as per this TGS is equal to 0.01, 0.02, 0.03 and 0.04, okay, because this is the negative bias over here, okay. This is the output characteristics of a thermal transistor, and then we try to study the transfer characteristics also, okay, for this particular part, that what is the transfer characteristics in this case. Yeah, the transfer characteristics, it means that we have to keep this constant and we have to vary this voltage, this temperature between these two junctions. Okay, and during this part, okay, we have the transfer characteristics like this, Yeah, and hence we have the complete set of a thermal transistor characteristics, that is the transfer characteristics and the output characteristics. The points over here, okay, on these parts obtained through our simulation, and the square box, okay, in this part is the intersects of these and the simulated curve, okay. So there is a good agreement with this. Not only this, based on this we try to, okay, give a common relation to explain this characteristics curve, like Shockley's equation. The equation which we frame over here is this, very analogous to this, that is, the source current is given by the source saturated current into 1 minus, this is the temperature, that is the gate temperature, and this is the pinch off temperature, whole square, like JD is equal to IDD, okay, into 1 minus VDS upon VP in a fat circuit, in the fat circuit. And the results, okay, if you use this result and if you see our simulated results, okay, then it gives the very nice agreement over here, very nice agreement over here, okay. So then this, okay, we have also calculated the thermal parameters for this transistor model, thermal transistor model, okay, thermal resistance for the source, thermal resistance for the drain, okay, for various gate bias, okay, gate bias. And this particular part, thermal resistance increases of the order of 10⁻⁴, okay, as you increase the thermal gate bias. And this resistance is also increases, that is the drain resistance is also increases. Based on this, we have defined the thermal transconductance. It is seen that as you increase the thermal gate bias, that is negative bias on the gate increases, okay, the amplification factor mu increases. For the same transistor, okay, the amplification factor increases. Yeah. Then comes, see, to explain the importance of this thermal physics to the students or the laymen in the society, because what we are doing, okay, we are in the position to understand very clearly, but whether this problem is important or not, for that I used to explain with few points to the audience, okay, in the layman's structure. That is, we know that is about 90% of energy is consumed either for heating, through the heating or cooling, and hence it is required to know the basic features of the heat conduction. Yeah, we also know that is the solar energy is known only for the solar cell, solar cooker, solar heater, and solar dryer. Okay, in all these applications, the solar radiation, that is this, remains at the focus. Okay, that is the photons of different wavelengths. Okay, we have rarely, okay, and the maximum effort are to generate the electric power. We have not focused on the phonons coming out from the solar heating. Yeah, we also know the solar radiation hits up the surface exposed by it, and we are making the efforts either to protect or cool the surface. Yeah, we have neither made any rigorous efforts to use this heat or store this heat for its fruitful use at a later stage. Of course, these slides are to explain to the common audience, that is what we are doing, that is the conduction mechanism, heat conduction mechanism is really interesting subject. Yeah, and it is deserved to give the proper attention. We can use the heat generated by the processor to generate the electricity, which automatically provide the feedback power to the computer. Can we devise a heat conducting wire which can drags the heat which is already coming out from our laptop and the computer over here? Okay, if you put the hands, okay, just this, okay, or we are using the heat sink, then okay, from this you can go to this. Or if you can drag the heat generated by the processor of my laptop or a computer, I can serve the hot coffee or a tea to any visitor at my lab. Yeah. I am using my car to going my office. An engine of my car produces very large amount of heat, and we use to cool that engine by radiator or coolant. Yeah, we have devised very efficient radiators, heat exchangers. Okay, and instead of that, if I have any mechanism, okay, that I can plug with that particular heat exchanger, now if anyhow I store this heat, then I can use that heat to prepare or warm my lunch at the lunch hours in the office. Yeah, that is, if I have, let us say, a thermostat, a battery, thermal battery, I can put on the with that particular part, and I drive 1 hour. Yeah, similarly, while going back to the base, okay, I can even prepare a dinner for a 5 man, okay, 5 person, because whatever the heat generated by running an engine, okay, for a 1 hour, the energy will be sufficient to cook a dinner for a 5 person. Yeah. So this is only for the explaining the importance of the heat transport mechanism, another part, to the society. Yeah, I hope I have not taken the much more time. It means that the first most requirement to utilize the heat is to have the material which allows the control the heat flow or to retain the heat for a longer period of time. For this, I have to think very differently. Of course, okay, this is the picture from Xiamen University, China. Yeah, so all the four people from the Xiamen University are over here. Okay, and we have to focus now not on the photons nor on the electrons. We have to focus very carefully on the phonons. Yeah. So with that, I stop over here. Yeah. Thank you for your kind attention.
Any questions from the audience? I have one.
Yeah, definitely. Yeah.
You first.
Yeah. Yeah.
Okay. For the case of thermal transistor, what kind of reservoir you apply to the system?
We have applied the Langevin heat path. Langevin heat path. Of course, we tried with the Langevin as well as this two other thermostats also.
Okay. So in
Nuze-Hoover and the Langevin.
no problem. In comparison with the studies of by Bowery, and what is the advantage of your model here, or do you have some very different property in comparison his model?
In comparison to this model?
In comparison his Professor Bowery's
model.
Study.
Yeah. See, in the previous study of the transistor, they have explained only the two uses. That is the switching and the amplification part. Okay. They have not formulated the other part. Okay. I will go back. Yeah. This part. Okay. They have studied only this kind of things. They have not studied the thermal transistor characteristics, whether the output characteristics or the transfer characteristics. Okay. Even they are unable to explain that saturation part is obtained, okay, through this. And the proper equation which we have given over here, okay, at this juncture, yeah, this equation, yeah, is not known so far. Yes.
Okay, now let's, since we're already ahead of schedule, let's thank the speaker again.
Yeah. Oh.